Deploying machine learning models is a crucial step in making your algorithms useful beyond the confines of a notebook. FastAPI, a modern Python framework, streamlines this process by offering high-performance automatic API documentation and robust input validation. In this video, we'll explore how FastAPI helps package trained models behind APIs, enabling web apps, mobile apps, dashboards, and other systems to send input data and receive predictions reliably. We'll walk through the entire workflow from training a model to deploying it in a production environment, highlighting best practices and common pitfalls along the way. Machine learning model is only valuable when it can accept real-world input and return predictions reliably. Deployment ensures your model operates in an environment where requests, latency, logging, and updates are managed carefully. FastAPI fits perfectly at this stage, converting Python inference code into a production-style web service with minimal boilerplate. By separating the trained model, preprocessing logic, API layer, runtime dependencies, and deployment target, you improve maintainability and make it easier to update or replace models without redesigning the entire application. FastAPI stands out among Python frameworks for ML deployment due to its use of modern Python type hints, which make request validation cleaner and more robust. It automatically generates interactive API documentation, allowing developers to test endpoints directly from the browser. FastAPI's high performance is suitable for real-time inference, and its clear routing structure simplifies endpoint management. Integration with Docker and cloud workflows is straightforward, making FastAPI a top choice for both prototyping and production deployments. Model deployment involves exposing a trained model to external users or applications in a controlled execution environment. The deployment layer receives input data, converts it into the format expected by the model, runs inference, and returns predictions in a user-friendly structure like JSON. There are three common serving styles: batch inference, online or real-time inference, and streaming inference. FastAPI excels at online inference, where each request receives an immediate prediction response, making it ideal for applications like fraud detection and recommender systems. Typical FastAPI-based ML serving system follows a clear architecture. First, train the model using frameworks like Scikit-learn, TensorFlow, or PyTorch. Next, save the model using methods such as joblib or pickle. Then build a FastAPI application that loads the model once at startup, define request schemas with Pydantic, and create prediction and health check endpoints. The app runs locally with Unicorn, is packaged with Docker, and finally deployed to a server or cloud platform. This separation between training and serving environments ensures stability and predictable runtime behavior. Start with training a simple Scikit-learn model. Using the iris dataset, we split the data, create a pipeline with a scaler and classifier, fit the model, and save it as model (pkl). Saving the full preprocessing and model pipeline is crucial, as it ensures the same transformations are applied during both training and prediction. This approach reduces errors and makes the deployment process smoother, especially when dealing with real-world input data. After training, the model is saved using joblib. This step creates a model (pkl) file that contains both the preprocessing steps and the classifier. By packaging preprocessing with the model, you ensure that incoming data is handled consistently, reducing the risk of mismatches between training and inference. This practice is especially important for production deployments where reliability is key. Next, we build the FastAPI application. The app loads the model once at startup, defines a Pydantic schema for input validation, and exposes endpoints for home, health, and prediction. This structure follows best practices for serving ML models, ensuring that the API is robust, easy to test, and ready for integration with other systems. FastAPI's automatic documentation makes it simple to explore and test endpoints during development. Using Pydantic, we define a typed input schema for the prediction endpoint. This schema ensures that incoming data matches the expected format, catching errors early and improving reliability. For the iris model, the schema includes fields for sepal length, sepal width, petal length, and petal width, all as floats. This approach makes the API robust against data type mismatches and simplifies debugging. Prediction endpoint receives input data, converts it into a NumPy array, and runs inference using the loaded model. The result is returned as a JSON object, making it easy for clients to consume. This pattern is widely used in ML deployment tutorials and ensures that the model is only loaded once, improving performance and reducing latency. FastAPI's structure makes it simple to add additional endpoints, such as health checks or metadata. To run the FastAPI app, you need to install several dependencies: FastAPI, Unicorn, Scikit-learn, joblib, NumPy, and Pydantic. These packages are listed in requirements, txt, making it easy to set up the environment. Installing dependencies with pip ensures that your app has everything it needs to run smoothly both locally and in production. FastAPI applications are typically run with Unicorn, an ASGI server. Starting the server locally with Unicorn app reload allows you to test the API in real time. The service runs on a default port and exposes auto-generated documentation at docs, which is extremely useful for testing prediction requests during development. This interactive testing experience is one of FastAPI's strongest advantages. Test the prediction endpoint, open the browser, and navigate to docs. Here you can send JSON inputs such as sepal length, sepal width, petal length, and petal width. The API returns a prediction as JSON, making it easy to verify that the model is working correctly. This hands-on testing is invaluable for classroom demonstrations and rapid development. Clean project structure improves readability and scalability. For beginners, a simple layout includes app, py, train model, py model, pkl, requirements, txt, and Dockerfile. As projects grow, it's better to separate routes, schemas, services, configuration, and model loading code into different modules. This modular approach makes the codebase easier to maintain and extend. Docker is essential for packaging the application and its dependencies, ensuring consistent operation across different systems. In ML deployment, Docker helps manage package versions, which is critical for reproducibility. Creating a Docker file specifies the base image, working directory, dependencies, and startup command. Building and running the container matches common FastAPI deployment workflows, preparing the app for cloud platforms like AWS, Azure, or GCP. Build the Docker image, use Docker build FastAPI ML app. This command packages the application dependencies and model into a container. Running the container with Docker run 8000 FastAPI ML app exposes the API on port 8000, making it accessible for testing and integration. This workflow is standard for FastAPI deployments and prepares the app for further publishing to cloud platforms. Production deployment requires more than just a working prediction endpoint. Good systems include a health endpoint for monitoring, input validation using Pydantic, logging for requests and failures, version models for rollback, separation of training and serving code, environment-based configuration, and monitoring for drift and prediction quality. FastAPI best practices also recommend cleaner project organization and strong validation rules for request schema. Health endpoint is essential for service monitoring. It allows external systems to check if the API is running and responding correctly. FastAPI makes it easy to add such endpoints, improving reliability and making the service easier to integrate with monitoring tools. This practice is standard in production deployments and helps catch issues early. Input validation using Pydantic ensures that incoming data matches the expected format and types. This reduces errors, improves reliability, and makes debugging easier. FastAPI's integration with Pydantic allows you to define schemas that catch issues before they reach the model, protecting against common mistakes like data type mismatches. Logging is crucial for tracking requests, latency, and failures. It helps diagnose issues, monitor performance, and improve the quality of predictions. FastAPI supports logging out of the box, and integrating additional monitoring tools is straightforward. Monitoring for drift, latency, and prediction quality ensures that the deployed model continues to perform well over time. Versioning models allows you to roll back to previous releases if issues arise. This practice is essential for maintaining reliability in production environments. By keeping models versioned and separating training from serving code, you make updates safer and easier to manage. FastAPI's modular structure supports this approach, making it simple to deploy new models without disrupting the service. Using environment-based configuration instead of hard-coded secrets improves security and flexibility. FastAPI supports environment variables, making it easy to manage settings for different deployment targets. This practice is especially important when deploying to cloud platforms where secrets and configuration must be handled carefully. Monitoring for drift, latency, and prediction quality ensures that your model continues to perform well as data changes. FastAPI makes it easy to integrate monitoring tools and collect metrics, helping you catch issues early and maintain high-quality predictions. This practice is essential for long-term reliability and performance. Organizing your project with clear separation of routes, schemas, services, configuration, and model loading code improves maintainability and scalability. FastAPI's structure supports modular organization, making it easy to extend the codebase as your application grows. This approach is recommended for both small projects and large production systems. Managing resources at startup and shutdown is important for production reliability. FastAPI supports lifecycle events, allowing you to initialize resources like models, database connections, or logging systems when the app starts, and clean up when it shuts down. This practice ensures that resources are used efficiently and reduces the risk of errors during deployment. Strong validation rules for request schemas protect your API from invalid input and improve reliability. FastAPI's integration with Pydantic makes it easy to define and enforce these rules, catching errors before they reach the model. This approach is essential for production deployments where robustness is key. FastAPI structure can be adapted to serve deep learning models as well. For TensorFlow or PyTorch deployments, the main differences are the file format, preprocessing pipeline, and inference function. The API layer remains the same, using endpoint-based approaches for prediction and health checks. This flexibility makes FastAPI suitable for a wide range of ML applications. For TensorFlow or Keras models, load the model with Keras models load model. The preprocessing pipeline and inference function may differ, but the FastAPI app structure remains the same. This approach allows you to serve deep learning models with minimal changes to the API code, making it easy to upgrade or switch frameworks as needed. For PyTorch models, load weights with TorchLoad and set the model to evaluation mode. The API layer still uses FastAPI endpoints for prediction and health checks. This consistency makes it easy to serve models from different frameworks, supporting a variety of ML use cases and deployment scenarios. ONNX provides a framework-independent way to serve models. Using ONNX runtime, you can deploy models trained in different frameworks with a unified inference pipeline. FastAPI's endpoint structure remains the same, making it easy to integrate ONNX models into your deployment workflow. Beginners often face several common issues when deploying ML models with FastAPI. These include model file not found due to incorrect working directory, missing preprocessing and inference code, request data type mismatches, dependency version conflicts, and loading the model on every request instead of once at startup. Addressing these errors early improves reliability and makes the deployment process smoother. Most deployment errors can be prevented by saving a full pipeline, pinning dependencies and requirements, TXT, and testing the API locally through before containerization. FastAPI's structure and automatic documentation make it easy to catch issues early, improving reliability and reducing debugging time. Swagger UI, auto-generated by FastAPI, provides an interactive interface for testing endpoints. You can send sample input, receive predictions, and verify that the API works as expected. This feature is invaluable for rapid development, classroom demonstrations, and debugging during deployment. Containerizing your FastAPI app with Docker ensures consistent operation across different systems and simplifies deployment to cloud platforms. By packaging dependencies and the model together, you reduce the risk of version conflicts and improve reproducibility. This approach is standard in modern ML deployment workflows. Deploying your FastAPI app to cloud platforms like AWS, Azure, or GCP is straightforward once the app is containerized. These platforms support Docker containers, making it easy to scale, monitor, and manage your ML services. FastAPI's structure and best practices prepare your app for seamless cloud integration. FastAPI's high performance and clear routing structure make it easy to scale your API as demand grows. By containerizing the app and deploying to cloud platforms, you can add more instances, balance load, and monitor performance. This scalability is essential for production ML services. Once you master the basic workflow, FastAPI can be extended to advanced use cases such as deep learning APIs, asynchronous inference, model monitoring, and ML ops pipelines. The same endpoint-based structure supports these scenarios, making FastAPI a versatile framework for ML deployment. FastAPI supports asynchronous endpoints, allowing you to handle inference requests concurrently. This feature improves performance for high-demand applications and supports real-time prediction scenarios. Asynchronous inference is particularly useful for large models or when integrating with external services. Monitoring deployed models is essential for maintaining performance and reliability. FastAPI makes it easy to integrate monitoring tools, collect metrics, and track prediction quality. This practice ensures that your model continues to deliver accurate results and helps identify issues before they impact users. FastAPI can be integrated into ML ops pipelines, supporting automated deployment, monitoring, and management of ML models. By following best practices in modular organization, you prepare your app for seamless integration with CI/CD tools, cloud platforms, and monitoring systems. This approach supports continuous improvement and reliable operation. Good learning sequence for deploying ML models with FastAPI is: train a small model, save it, build a FastAPI prediction service, test it in Swagger UI, package it with Docker, and deploy to a cloud environment. Once you understand this workflow, you can extend it to more advanced use cases supporting deep learning, asynchronous inference, and robust monitoring. FastAPI is simple enough for hands-on learning and strong enough to support production-style patterns. By practicing the workflow from training to deployment, you gain valuable experience and prepare for real-world ML projects. FastAPI's automatic documentation and modular structure make it ideal for both beginners and advanced users. FastAPI's features, automatic validation, interactive documentation, Docker integration, and modular organization make it a strong framework for production ML deployment. By following best practices and testing thoroughly, you ensure that your deployed models are reliable, scalable, and easy to maintain. Once you're comfortable with the basics, FastAPI can be extended to support more complex workflows, including deep learning APIs, asynchronous endpoints, and integration with monitoring and ML ops tools. Its flexibility and performance make it suitable for a wide range of ML deployment scenarios, from classroom DMOS to enterprise production systems. Deploying machine learning models with FastAPI provides a clean, modern path from trained Python models to deployable inference APIs. Whether you're a student, researcher, or practitioner, FastAPI offers a practical, scalable solution for serving models in production. By mastering the workflow and best practices, you're ready to tackle advanced ML deployment challenges and build reliable, high-performance services.